this video, we are going to implement an autocomplete autoencoder on MNIST dataset using TensorFlow library. So follow us in this video. First, we need to import the required libraries. Here, in this part of the code, you can see how we have imported the required libraries such as the NumPy library, Matplotlib, and TensorFlow. We have also imported the MNIST dataset as the input data from the TensorFlow library, as you can see here. It is actually imported from the examples and the tutorial parts of this library. In this part, we have loaded the dataset in the MNIST data, as you can see here, which will have a train images and the test images part. So the dimensions of the training images and the test images are shown here. As mentioned before, the MNIST dataset includes images of different digits, and these images have the size equal to 28 times 28. The training set has 55,000 samples, while the test set has 10,000 samples. These images are in the vectorized format by default, meaning that they have one dimension with 784 elements instead of two dimensions of the size 28 times 28. So you can see the dimensions is 55,000 and samples and 784 features and 10,000 and 784 features for the testing set. Here in this part, we have shown an example of this dataset. A digit from the training set is shown here, while we have also shown a digit from the test set here. In order to see these images, we need to reshape the vectorized image into 28 times 28 because by default they are in the vectorized format, and we need to reshape them to a matrix format in order to see them here. Moving on to this part of the code, we will start building our desirable model for the 3-layer undercomplete autoencoder. Since each digit image would have 784 components, the input size and the output size are equal to 784, as you can see here. We would like to decrease the features from 784 to 196, which offers around 75% compression. So we are actually keeping about 25% of the most important features and discarding the rest of them. The activation function that we have used is the famous ReLU activation function. By setting the initializer, we would like to return an initializer that generates tensors without scale invariance. You can see it here. When initializing a deep network, it is in principle advantageous to keep the scale of the input variance constant, so it does not explode or diminish by reaching the final layer. We will also define the init to initialize the global variables. I have commented it here because I will redefine it in the next part of the code. Here in this part, we have defined a placeholder that would keep the input values in it when we run the session. The type of the values that it would accept are of type float. We have also defined the weight variable as a tensor variable to keep the weights in it in the hidden layer, as you can see here. The tensor weight 2, which is defined here, will keep the weights between the hidden layer and the output layer that can be used in the future in order to show the compressed version of the data. In the same way, tensor variables called bias and bias2 are also defined that will keep the values of the biases before the hidden layer and after the hidden layer in them. You can see these variables defined here. The hidden layer is formed by defining the matrix multiplication matmul of the TensorFlow library between the inputs, which is called AE or auto-encoder inputs, and the weights here. And the output of the hidden layer would be called the HID. And it will be the output we will get after applying the ReLU activation function on the summation of the multiplication result with the bias. Here we have done the same thing. The output layer is formed in the same way as I said. The multiplication of the output of the hidden layer with the weights are stored in mult2, that you can see. And then the activation function ReLU is applied to the summation of the multiplication and the bias. That would form the output that we have. In this part of the code, we have defined the learning rate to be 0.01. You can see here. And the loss function is defined as the mean square error between the output and the input. This is the square and this is the mean of the error, which is the difference between the output and the input that we have. The optimizer is said to be the ADAM optimizer, ADAM. You can see it here. Then we would define the training as the minimization of the MSE loss function using this optimizer, as you can see here. Now the overall outline of the model is complete and we only need to start a session to begin the training. Nothing is done yet since we have not started a session, so even the tensor variables do not contain any values in them. We must keep in mind that in order to start any kind of computation or memory allocation in TensorFlow, we need to start a session. This is what we are going to do here in this part of the code. The number of the epochs is set to 10. And as I said, we have used the initializer. We have defined the initializer for the global variables. The batch size is set to 100. So each time that we will do the training, we would do the training on around 100 training samples. Since we have 55,000 training samples here, the number of the batches of size 100 would be 550. This is what we have found here. In order to test to see whether the autoencoder is working properly or not, we have considered 10 test samples as well, as you can see here. Since we are not using the labels of the data anywhere here, this is still considered as an unsupervised learning algorithm. Then we run the session here. We run it and we initialize the variables. And in each epoch, we run the training for 550 batches of training samples. So this is the place where we need to input the data and put it in the placeholder that we have already defined. So we use the feeddict that you can see here to feed the placeholder with our actual data, or simply the training samples, the AE inputs. The training loss is shown here for each batch in each epoch. You can see the training loss in each batch and in each epoch. The results here hold the output of the results that you can see here. They hold the output of the network and also the output of the hidden layer when we feed the network with the test data. So you can see these are the values of the output and these are the outputs of the hidden layer. And we have used the feeddict in order to feed the placeholder with our actual data, which is the test data here, and also the test data here. These are all the training losses. Here, in this part of the code, we have used the subplot property of the matplotlib library to show the results of the test data in the lower part and compared them to the actual images that were fed to the network as input. So we have fed the test data, 10 test samples, to the autoencoders that you can see here. These are the inputs of the test samples, and these are the reconstructed test samples that we have in the output. As you can see, the output is kind of blurry since the input data is passing through a bottleneck because we are compressing the data once, and because it is once encoded, so there would be kind of some kind of error while reconstructing the image. So we can see that the output is kind of blurry. So in this last part of the code, we have plotted the output of the hidden layer to see what do the compressed images look like, as you can see here. As you can see, by losing around 75% of the data, a lot of information is missing because we are losing around 75% of the features, and we are only keeping the 25% of the most important parts. In this case, it will give us no understanding of the data, so we cannot figure out what digits they are showing because we are losing a lot of information in the bottleneck that we are creating. So it means that MNIST dataset is not that compressible, such that it would not let us compress it up to around like 75%. But this is not the case with all of the data that we have. In some of the data sets which are compressible, we would be able to compress even more than 75%. So this is not true for all of the data set. It is different from data set to data set. You need to increase the number of the neurons in the hidden layer here in this specific example with this specific data set in order to keep more information and in order to keep more features that are determinant for our data set.